Good evening, children. Today we are doing ethers. Ethers are organic compound with this functional group ROR, or it can be ROR dash. When it is ROR, it is symmetrical ether. When it is ROR dash, it is unsymmetrical ether. So here we have example of symmetrical and unsymmetrical ether. Let us do the IUPAC naming of these compounds. Ethers are named as alkoxy alkane. This is a prefix, this is a word root, and this is the primary suffix. So here its name will be methoxy. This is methoxy part. Methoxy, one carbon atom chain. So methoxymethane. The common name of this compound is dimethyl ether. The IUPAC name of this compound, smaller alkyl group should be in prefix. So it should be again methoxy ethane. So here it is symmetrical, so it will be ethoxy ethane. The chain is 1, 2. Here the chain is 1, 2. In this case, if I name it methoxy, this is 1, 2, 3. Methoxypropane. The name is not complete. It should be named as, because it is at one place, so 1 methoxypropane. And in this case, this is 1, 2, 3. So its name will be 2-methoxypropane. And this is one phenolic ether. So its name will be methoxybenzene. So this is how ethers are named. Now let us talk about preparation of ether. So the first method of preparation is we can prepare it from alcohols. So say if I take methyl alcohol, if it is treated with concentrated sulfuric acid at a temperature of 440 Kelvin, then we get CS3O CS3. This ether we get. Actually here two molecules of this take part, and there occurs loss of water. So that this is a complete balanced equation. Now we need to know the mechanism of this reaction, how ethers is formed. So let us talk about mechanism. Step 1, there occurs protonation of, so CS3O8 and lone pair H plus, is H plus coming from acid, so CS3O8. So protonation has taken place, O will become plus, And in step 2, what will happen is a second molecule of alcohol, will act as nucleophile, and it will attack at this carbon. So I am showing it here only. Second molecule of alcohol will act as a nucleophile, will attack here, and simultaneously this bond will break. So two things are happening simultaneously. This bond is getting formed, this bond is getting broken. So here the attack is SN2 attack. So SN2 attack will give us this one, CH3 O CH3 CH3O CH3, and this H, suppose I am writing it here, and there is one lone pair. So this is second step. Water is removed. And the third step, the step 3, since this O plus is highly electronegative, this bond electron will be attracted by oxygen, and this proton will be lost. So I am doing it from here only. So minus proton is getting lost, and we get this ether. So this is a mechanism of formation of ether from alcohol. So if we have this alcohol at concentrated sulfuric acid at this temperature, so we will get this ether, CH3 CH2 O CH2 CH3. So this ether we will get. Now there is a problem. One problem is there with this method. We cannot prepare unsymmetrical ether. We cannot prepare unsymmetrical ether by this method. This is one problem with this method. And there is another problem. Even symmetrical ether of this type, cannot be prepared by this method. Here just I am giving you a hint here. If you want to prepare this ether by this method, then we have to take tertiary alcohol. And with tertiary alcohol, there will not happen substitution. Tertiary substance will not undergo substitution, they will prefer to undergo elimination. That's why such ethers also cannot be made by this method. Now let us consider another method, which is a much better method, and we can even prepare unsymmetrical ether by this method, and that is the name reaction is involved. That is so second method is by Williamsons ether synthesis. Williamsons ether synthesis. So here, what we have to take, we have to take an alkyl halide, and the alkyl halide has to be 1 degree primary, and a sodium alkoxide, so O minus Na plus, and so sodium alkoxide. So alkyl halide 1 degree and sodium alkoxide, and there will be SN2 attack, and we will get R O R dash plus NaX. So this is the basic scheme of reaction in case of Williamsons ether synthesis to get ether. Suppose we want to prepare this ether. We want to prepare this ether by Williamsons ether synthesis. So you have to understand, there are two parts. This is one part, this is another part. And since we have to take a 1 degree compound, 1 degree halide, so the reagent that we have to take will be CH3X, say it is CH3I plus alkoxide of this part, so it will be Na plus O minus, so this and this will give us this ether. Now a question can come, a question can arise here. What will happen if we take it other way round? Other way round means, suppose if I take CH3C, if we take this one plus Na plus O minus CH3, that means if we take a 3 degree halide, then of course we will not get this ether. What we will get here, in this case, since it is 3 degree compound, elimination will be dominating here. Elimination will take place. This substance will play the role of a base, so beta elimination will take place here, and the product that we will get will be CH3, C, double bond CH2, CH3. So beta elimination will take place, we will get alkene. So we won't get the required ether. So remember, in Williamsons, the halo compound has to be always 1 degree. Okay, now suppose when you are asked to prepare this ether by Williamsons ether synthesis. Phenolic ether you are asked to prepare. So what should be the reagent that you will be taking? So obviously the reagent that you will take will be CH3I primary, and the alkoxide ion will be O minus benzene ring Na plus. So this will give us this phenolic ether. It cannot be the other way around. Now coming to the properties of ether. Mm, ethers are very less reactive substance. That is the reason why they often find use as solvent in organic reaction. And one chemical property which is very important, we need to discuss. We're going to discuss here is reaction with HX. The reaction of HX with ether. So suppose RO, this is an ether plus HX. What happens is this bond gets cleaved. This bond gets broken, and we get here R X plus R O H. So we will get a halo compound and alcohol. Now let me take a genuine example of ether. Say CH3O CH2 CH3 plus HI, and if it is heated, so the product will be now the smaller alkyl group side, that bond breaks if it is unsymmetrical. That you have to remember, smaller alkyl group side breaks. So if this bond breaks, then it will be CH3I as one product, CH3I, because with O, H will go. With O, H will go, and another product will be CH3, CH2, OH. So you should always remember smaller alkyl side group. And let us discuss the mechanism of this reaction. How can this be explained? Mechanism, let us do the mechanism. So this is the ether CH3O CH2 CH3, and first step once again is protonation. This HI will supply the proton, and CH3O CH2 CH3H. So this will be formed in the first step. Now in the second step, this I minus will act as a nucleophile. I am showing it here only. This I minus will act as a nucleophile in the second step. This was the first step. And now I minus attacking here and I minus attacking here. Now I minus will prefer attacking here. Why not at this carbon? Because this I minus will experience steric hindrance because of this bulky CH3 group. So this I minus will not attack here, it will attack at smaller alkyl group. So when I minus attacks here, so obviously this bond will break and it will come here. So I minus is attacking at CH3, and the product form will be CH3I plus this CH3 CH2 OH. So this is how we can explain the formation of product. Very simple two-step mechanism. First step is protonation, and second step is nucleophilic attack, and this is attacking simultaneously, this is breaking. So obviously this is SN2 attack, you have to remember, SN2 attack. One more thing let me tell you here is that this alcohol that is formed in the product can further react with HI if HI is in excess. If HI is in excess, this alcohol can further react with HI. This reaction you have studied already, and will give us CS3 CH2I plus water. So this is how cleavage takes place. Now, suppose let me discuss this question now. So this is SN2 attack. Nucleophile attacks a smaller alkyl group. This is what we can see from here. Now, how can you explain the formation of these products by this reaction? Say this reaction, CS3O C CS3 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 plus HI, heat, and the product we get is CS3 C CS3 CS3 I plus CS3OH. This is the product that we get in this reaction. What we have said just now previously, it is not being followed here. So what is happening here, that we have to explain, and let me write a mechanism in support of this product. So the mechanism for this reaction is once again, first step is protonation. So CS3O C CS3 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 going pair. First step is protonation. So first is protonation, and now here what happens is, in the second step, this is first step. In the second step, there occurs ionization. And this bond breaks. The electron goes like this. Why it happens here different from the previous year? Because this can give a very stable carbocation. That's why here ionization will take place before nucleophile can attack. So this ionization will give us CS3OH as one product and a carbocation C CS3 CS3 CS3. So a carbocation results. Of course, this is a 3-degree carbocation, you can see. So the reason why this is formed is because it is highly stable, it being 3-degree carbocation. So that is the reason why this mechanism, it is SN1 mechanism. And after the formation of carbocation, in the third step, nucleophile will attack, and we will get this product. So that you see the product, these two products that we are getting is also here. So we are able to explain the formation of these two products very nicely by this SN1 mechanism. So what is happening here, let me tell once again. First step is protonation. Second step is not nucleophilic attack, unlike the previous case. Second step is ionization leading to formation of carbocation, and third step there is nucleophilic attack resulting in the product. SN1 mechanism. So a question here which comes very frequently in exam to predict the product. Say this case. This case, we are asked to predict the product. So here the answer, I am telling the answer. The answer here will be CH2I plus CH3OH. This will be the answer, and here this reaction goes by SN1 mechanism. It will go by SN1 mechanism. I am giving you a hint because here from this ether, this carbocation which is very stable can be formed. That's why it goes by SN1, and this is the product. Okay, coming to the case of phenolic ether. Coming to the case of phenolic ether, say phenolic ether, and here plus R effect will be there. Plus R effect, this lone pair coming here, and this bond will. So the contributing structures, okay, will be like this. The 2 electrons here, minus here, double bond pair, O here, R here, one lone pair, O will plus. So this is the structure that will result, and in the same way, what will happen is the next structure, this bond will come here, this one. So, resonating structure of phenolic ether tells us that there is more electron density at ortho and para place. So, when we carry out electrophilic substitution reaction of this compound, say nitration of this compound, or Pregel-Kraft alkylation of this compound, Pregel-Kraft acylation of this compound, or sulfonation of this compound, which we have discussed in the previous chapter, we will get product as ortho and para product will be getting, and para product will be dominating out of the two. So this electrophilic substitution reactions I am not discussing because this we have already discussed before. You can easily understand. You have to just remember the reactions. So this much is there for ether. And we have, so in this way, completed the second chapter. Tomorrow in our class we will be doing some question answers on this chapter. Till then, good night.